Hi, how's it going? Hope it's going well. Well, in this video I'm going to talk about the expected value of a discrete random variable. Now, as soon as you realise that the expected value and the mean are the same thing, then you're going to get on with the section a lot better, okay? So the mean value is actually the same as the expected value. Let me give you an example of that. Suppose a class of students do a test and the mean score is, let's just say, 75%, okay? If we talk about 75% as being an expected value, what we're actually saying is that if somebody had missed the test and then they took it, you might expect them to get around 75%, okay? Because that's the mean value of the class. It's an expected value of a general person that you select at random from the class, okay? And that's really what we're going to be talking about in this section. We're going to talk about expected values, we're talking about a mean value. So the first thing I'm actually writing down is the shorthand notation for expected value of a random function is e of x, okay? And that is just the same as the mean, mu. And in previous sections, we looked at mu for being the mean, okay? And the way it's calculated is very simple. And I'm going to illustrate it with this rather straightforward situation where you've got a probability distribution, capital X of course, for a fair six-sided die. Okay, so here's the table, probability distribution as a table, and so you've got the individual outcomes being 1, 2, 3, 4, 5, 6 on this fair six-sided die. And as before, we've seen that it's a uniform distribution, probability of each one happening is 1/6. Okay, now forget probability for the moment, try and calculate what the mean score on the die is. In other words, you roll the die, what's the mean score? Well, of course, to work out the mean of any set of numbers, you add all the numbers together and divide by how many values there are. So you do 1 plus 2 plus 3 plus 4 plus 5 plus 6, and you divide by 6. Okay. And what answer do you get? Well, if you calculate it, you get 3.5. Okay. You get 3.5, that's the mean. Now you can do exactly the same thing for working out the expected value with a set of probability values from the table like this. Okay. All you need to do is you just multiply each of the individual x values by the probabilities and add them together. Okay. So the working just looks like this effectively. So you get 1 times the 6th, 2 times the 6th, 3 times the 6th, 4 times the 6th, 5 times the 6th, 6 times the 6th, and then just add them together. Okay. And you get exactly the same answer. You get 3.5. Now, why does that work? Just contrast the working from two different scenarios. So a year 7 class, maybe, they've been asked to work out the mean of the numbers 1, 2, 3, 4, 5, 6. That's the working they'll show. 1 plus 2 plus 3 plus 4 plus 5 plus 6, all divided by 6. Okay. In terms of the A-level class that we're in, doing statistics, S1, this is how we do it. Okay. 1, 6 plus 2, 6 plus 3, 6. Can you see the working's exactly the same? Because of the denominator, really, isn't it? Okay. That's just rather a simple example showing you how the calculations for working out the mean of a set of numbers and working out an expected value, we know the probabilities, is exactly the same. Okay? And it's as straightforward as that. So, summing up, sorry for the pun there, didn't mean that. In summary, I can't help myself, the expected value of 3.5 means every time you roll the die, expect 3.5. Of course, that's not possible because there's no 3.5 as a number, but if you take 2 dice, okay, then the expected value is 7. Work it out if you want using the same sort of technique. Of course, the probabilities of getting a score of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 are going to be different. They're going to vary. Okay, but when you do the calculation, trust me, you will get 7. And then in context, that kind of makes sense, doesn't it? We can say that when you roll any 2 fair dice, you'll get a score of 7. That's the most likely score, and that's what we call the expected score. Okay, let's move on to another example. I'm going to show you. I'm going to introduce to you here an expected value of x squared. Now for the moment, just go with it. It will become very important later on. Little hint when we look at variance. Remember variance? The standard deviation and all of that from earlier on? Yeah. It's going to be helpful for us if we can work out an expected value of x squared. Now just a little note here, if x is a discrete random variable, you can start abbreviating these if you want because DRV takes a long time to write down. If x is a discrete random variable, and so is x squared, obviously a discrete number squared also gives you a discrete number. Okay. We can also find the expected value of x squared, and I'm going to do that quite simply using the table that we just had. So, for example, with the dice rolling, okay, numbers 1 to 6, all you do is just square these values, which is simple. So it doesn't have to be about rolling dice. It could be any discrete random variable. Okay, you've got your lowercase values of x for your actual outcomes. You just square those values. The probabilities of each individual value is still the same. So crucially, the probability of x is the probability of each one of these. Okay, but what you're doing instead is, as the formula here suggests, you are multiplying the squared values by each probability. So in other words, our calculation would be 1 times 1/6 plus 4 times a sixth plus 9 times a sixth, 16 times a sixth, 25 times a sixth, 36 times a sixth. Okay, and we call that the expected value of x squared. Okay, in its own, it doesn't really mean much. Okay, but as I said, it will become very useful for when we go on to doing the variance of x. Okay, which is helpful because it's about measure of spread, isn't it? As I said, it's about standard deviation. So knowing that the expected value of x is 9/1/6 or 15 1/6 will come in quite handy later on. Okay. Well, that is it. That's my introduction to expected values. I'm hoping you found it useful. I'll see you shortly. There's another video coming up separately on variance.